Welcome to G Fun Facts Online. Imagine the Earth's skin, the very crust beneath our feet, slowly unzipping itself down the middle. This isn't science fiction. It's a process happening right now, in perpetual darkness, under the crushing pressure of the deep ocean. Today, we're taking an expedition into the abyss to listen to the planet's heartbeat, to witness the birth of our world's crust in spectacular slow motion, all through the incredible science of marine seismology. For centuries, the ocean floor was a complete mystery, a blank canvas. But the advent of marine geophysics has peeled back that veil, revealing a world of towering underwater mountains, deep trenches, and incredible volcanic activity. At the heart of this exploration is marine seismology, a field dedicated to probing the deep earth beneath the waves. So how do we see what's happening miles below the seafloor? The primary method is a sophisticated form of echolocation called a marine seismic survey. A research vessel uses a sound source, typically an array of what are called air guns, to release a powerful pulse of energy down into the water. This sound travels through the water column, penetrates the seafloor, and then reflects off the various layers of rock and sediment beneath. Think of it like a planetary-scale ultrasound. Just as a doctor uses sound waves to see inside the human body, geophysicists use them to see inside the Earth. The returning echoes are recorded by incredibly sensitive underwater microphones, called hydrophones. These are often towed behind the research vessel in long cables or streamers that can be several kilometers long. By analyzing the time it takes for these sound waves to return and the strength of the signal, scientists can construct a remarkably detailed image of the subsurface. This technology is incredibly versatile. It's instrumental in exploring for oil and gas reserves, identifying potential reservoirs deep beneath the seabed. It's also used for mineral exploration, monitoring the environment, and assessing geological hazards like underwater earthquakes and tsunamis. It even plays a vital role in climate change research, allowing scientists to read the history of our planet's climate as it's been recorded in layers of sediment on the ocean floor. But perhaps the most profound contribution of marine seismology is the tangible, undeniable evidence it has provided for the theory of plate tectonics. It allows us to observe the process of seafloor spreading in unprecedented detail, witnessing the very fabric of our planet unzip at the seams. To eavesdrop on these deep earth processes requires a sophisticated toolkit. The workhorse of these surveys, the seismic source, has evolved over time. Early explorations actually used dynamite, but today's standard is the air gun. These devices work by rapidly releasing a bubble of highly compressed air into the water, creating a powerful pulse of sound. To make the sound beam more focused and powerful, multiple air guns are often fired together in a tuned array. The ears of the survey, as we mentioned, are the hydrophones. In a typical survey, hundreds or even thousands of them are arranged in those long streamers towed behind the ship. More advanced techniques, like 3D and 4D seismic surveys, use multiple streamers to create an even more detailed, dynamic picture of what's happening below. While towed streamers are perfect for mapping huge areas of the ocean floor, sometimes scientists need to listen closely to one specific spot for a long time. For this, they use another crucial tool, the ocean bottom seismometer, or OBS. As the name suggests, these are self-contained instruments that are dropped directly onto the seafloor. Housed in a protective sphere, an OBS contains a seismometer, a data logger, batteries, and an acoustic release that allows scientists to call it back to the surface after its mission is complete. The seismometer inside works on the principle of inertia. A heavy mass is suspended on a spring. When the Earth moves from a tremor or earthquake, the housing of the OBS moves with it, but for a brief moment, the heavy mass stays still due to its inertia. This relative motion generates a tiny electrical current, which is what the instrument measures and records. These OBS units are invaluable for studying earthquakes and the fine-scale structure of the crust, and they can be deployed for months or even over a year, providing a continuous record of seismic activity. It's this combination of powerful sound sources and sensitive listeners that allows scientists to piece together a comprehensive picture of the world beneath the waves. Now, let's talk about the biggest discovery this technology has led to: the unzipping of the Earth's crust, a process we call seafloor spreading. The concept that the Earth's crust is in constant, slow motion is a cornerstone of modern geology. The engine driving this is seafloor spreading, which occurs at the mid-ocean ridges. This is the longest mountain range on our planet, but it's almost entirely underwater. These vast chains of volcanoes wrap around the globe like the seams on a baseball. Mid-ocean ridges are what we call divergent plate boundaries, where the Earth's tectonic plates are pulling apart from each other. As the plates separate, magma from the mantle, the layer beneath the crust, rises to fill the gap. It erupts onto the seafloor as lava, which then cools and solidifies, forming brand new oceanic crust. This process is continuous. The newly formed crust is constantly being pushed away from the ridge as more magma wells up from below. This causes the seafloor to literally spread. The rate of spreading varies. At the mid-Atlantic ridge, it's a leisurely 2 to 5 centimeters per year, about the same speed your fingernails grow. But at the East Pacific rise, it's a more brisk 6 to 16 centimeters per year. This is what shapes the ocean basins and drives the continents apart. The evidence for this, provided by marine seismology, is incredibly compelling. One of the most striking pieces of evidence is the pattern of magnetic stripes on the ocean floor. Here's how it works. As the hot magma at the mid-ocean ridge cools, the magnetic minerals within the new rock align themselves with the Earth's magnetic field at that specific time, locking that direction in place. But the Earth's magnetic field has reversed its polarity many times throughout history. North becomes south, and south becomes north. This process creates a perfectly symmetrical pattern of normal and reversed magnetic stripes on either side of the ridge. Marine seismic surveys, combined with magnetic surveys, have mapped these stripes across the globe. They act like a giant barcode, providing a clear, readable record of the seafloor's creation and movement over millions of years. Another key piece of evidence is the age of the oceanic crust itself. Using seismic data to pinpoint the mid-ocean ridge, scientists have then collected rock samples at various distances from it. They confirm that the youngest rocks are always found right at the ridge crest, and they get progressively older the further you move away. This is exactly what you'd expect if new crust is being formed at the center and then moving outwards. Furthermore, advanced seismic surveys have allowed us to peer deep beneath the mid-ocean ridges and directly image the magma chambers that fuel this entire process. Studies at the East Pacific Rise, for example, have imaged a thin, molten sill of rock right beneath the ridge axis, giving us a direct glimpse of the engine of crustal formation. By combining all these lines of evidence, from the grand sweep of magnetic stripes to the fine details of crustal thickness, marine seismology has provided undeniable confirmation of seafloor spreading. It has allowed us to witness, in a very real sense, the unzipping of our planet. Of course, venturing into the deep ocean to listen to these secrets is an endeavor fraught with challenges. The marine environment is unforgiving. The sheer cost and logistical complexity of these surveys are immense. They require specialized research vessels that cost a fortune to operate, meaning every moment at sea is precious. The deep sea environment itself is a formidable obstacle. The immense pressure at the bottom of the ocean requires instruments to be housed in incredibly robust, pressure-resistant casings. And the ocean is a noisy place. The constant movement of waves and currents creates a huge amount of background noise that can interfere with the faint seismic signals scientists are trying to detect. Then there is one of the most significant challenges, which is a topic of considerable debate: the environmental impact of the surveys. The powerful sound waves generated by air guns can potentially harm marine life, from the smallest zooplankton to the largest whales. This has led to a growing focus on developing more environmentally friendly seismic sources and implementing strict mitigation measures, like having marine mammal observers on board to halt operations if animals get too close. Despite these challenges, the field of marine seismology has seen remarkable triumphs and advancements. The development of 3D and 4D seismic imaging has revolutionized our ability to visualize the subsurface. It's like going from a flat 2D X-ray to a full-motion 3D MRI of the Earth's crust. There have also been huge strides in the instruments themselves. Modern ocean bottom seismometers are becoming smaller, more powerful, and less expensive, allowing for the deployment of larger and denser arrays to get higher resolution data. And the processing of this data has been transformed by artificial intelligence and machine learning. These powerful computational tools can sift through vast amounts of information, identify subtle patterns, and improve the accuracy of our interpretations far beyond what a human could do alone. The future of marine seismology is bright. The quest for more environmentally benign seismic sources continues, with innovations like marine seismic vibrators, which produce a much gentler sound, showing great promise. The use of autonomous underwater vehicles, or AUVs, for data acquisition is also becoming more widespread, offering a more efficient and cost-effective way to explore the ocean depths. The journey of marine seismology is one of constant innovation and perseverance. For every obstacle encountered in the dark, cold depths, a new solution is devised. It's a testament to our enduring curiosity and our relentless pursuit of knowledge about the planet we call home. So the next time you look at a globe, remember that it's not a static object. It's a living, breathing planet. Continents are drifting, oceans are growing, and it's all driven by that slow, relentless unzipping of the Earth's crust. Thanks to the incredible science of marine seismology, we are no longer just living on our planet. We're listening to its deep, slow rumble and unlocking its secrets, one seismic pulse at a time. Thanks for listening to Fun Facts Online.